Hello everyone, Professor Brown here, and this is the lecture for Chapter 5, which covers the topic of stereoisomerism. Hello everyone, Professor Brown here, and this is the lecture for Chapter 5, which covers the topic of stereoisomerism. Here on this first slide, we have a definition of two different kinds of isomers. One we've covered pretty extensively at the beginning of the course, and that was our constitutional isomers. Constitutional isomers are molecules that have the same type and count of atoms. However, those atoms are connected or arranged differently from each other. At the end of the last chapter, we took our first look at what we're going to call stereoisomers. Stereoisomers are molecules that have the same molecular formula as well as constitution. However, they have different spatial arrangements. So there's the same number of atoms there, the same type of atoms there. They're all connected in the same arrangement. However, because of the way a bond or ring closes or is oriented, those atoms may be oriented different spatially in that atom or in that molecule. We got a good example here in cis and trans 1,2-dimethyl cyclohexane, which we took a look at the end of the last chapter. If you went around and looked and tried to count or tried to draw out a connection of these atoms to each other, you would find that they're all connected in the same order. However, these are different molecules. Because we've looked at how ring flips work, we know that you never can arrive at a situation where these two can be exactly superimposed upon each other because they are different. And even though they have the same connectivity, even though they have the same molecular formula, they are isomers of one another because of those spatial arrangements of those methyl groups above and below the ring, making these two molecules, as we say, stereoisomers of one another. Like I said, we took a look at the end of the last chapter at how rings can display cis and trans stereoisomerism, meaning you can have two different orientations where your substituents on your ring are either both above or below the ring, or one is above and one is below the ring. Double bonds or pi bonds also share this same locked in placeness, if you will, as the substituents on a ring. When you have a double bond in a molecule, that bond is not free to rotate like single bonds are because of the overlap of those pi bonds forming the bond. If you try to rotate it, the overlap between those pi bonds would break, which would be essentially breaking the bond. So pi bonds are locked in place, and we will have to describe how the substituents on that pi bond are oriented to one another. You can see two examples here on this slide. We have cis 2-butene and trans 2-butene. So if we take a look at the difference between those two stereoisomers, what we see is in cis 2-butene, the two big methyl groups are on the same side of the double bond as each other. In trans 2-butene, the two big methyl groups are on opposite sides of the bonds from one another. So these are the same molecule, they have the same connectivity, however they are different spatially, so they are stereoisomers of one another, and they are cis and trans stereoisomers of one another about that carbon-carbon double bond. Here we have a little bit more about alkene, cis and trans stereoisomerism. Alkene is the name that we give to molecules when that carbon-carbon double bond appears. We will learn about them in later chapters of the course, how to name them more specifically, etc., etc. But here we just want to take a look at the difference between cis and trans a little bit more closely around these double bonds. So like I said, the pi bonding causes the double bond to be locked in place. It can't rotate. So whatever you see drawn around that pi bond is how that molecule stays at that location constantly. It never changes from that orientation unless a chemical reaction takes place. Alkenes with substituents other than hydrogen on each side of the bond must be indicated as to the stereochemistry. Cis substituents are on the same side of the bond, and trans substituents are what is considered to be opposite sides of the bond. We'll learn later that if there are 3 or more substituents, so if there's only one hydrogen as one of the substituents on the double bond, there is a different system for naming them, and we'll get a little more in depth with that when we do the alkene chapter, but this time around, for right now, we're just trying to be able to differentiate between cis and trans. And you can see some examples up there in the pictures. We have the first one on the far left. On the top left is cis-2-octene, where we have the methyl group and then the rest of the chain on the same side of the double bond in cis-2-octene, and that's why it's considered cis. But in trans-2-octene, we can see that the methyl group goes in the down direction, whereas the rest of the long carbon chain is in the up direction, meaning they're on opposite sides of that double bond, and so that's trans-2-octene. And in 3D space, those molecules are locked in place at the double bond, and those cis and trans, they don't interconvert between one another. They are different molecules. That's why they are stereoisomers. You can see the difference there in cis and trans cinnamic acid. So cinnamic acid is obviously it's a common name, it's a non-IUPAC name, but both of those molecules exist and are different from each other because they are locked in place at that double bond where we show the cis and trans difference. Now you do have to be careful if one side of the double bond is hydrogens only, so the arrow is pointing to an sp2 carbon there that has a double bond and then would have 2 hydrogens bonded to it as well to fill out its valency. And because they're the same atom on that side of that double bond, you can't say whether the big substituents are cis and trans to 2 of the same hydrogens. So there is no stereoisomeric change at that position for that particular double bond. So if one side of the double bond has the same 2 substituents, there is no stereoisomerism at that position. Let me say that again. If the one side of a double bond has the same 2 substituents, and it doesn't matter if that's hydrogen or 2 methyl groups or 2 ethyl groups or 2 longer groups, if one side of the double bond has the exact same 2 substituents, there is no stereoisomerism at that position. So we have some examples here. We're going to try to determine whether these molecules are cis or trans about the double bond or about the ring, depending on what's present. In my first example, up here at the top left, I see a straight chain with a double bond kind of in the middle there. And to do these, I like to fill in my hydrogens. That helps me figure out where the tops and the bottoms of the double bonds are. So on this first molecule here, I might withdraw a hydrogen coming off the top, since that one's coming from going kind of down there, and then that substituent is going to the bottom, and so the hydrogen is going down here. So this chain here, this larger substituent here, is in kind of an up position, if you will, whereas this chain here, this larger substituent here, is in a down position. So this molecule would be considered a trans stereoisomer. In the next example here, I like to draw in my hydrogens. Got kind of a long one there. We'll replace it there as well. Hydrogen, hydrogen. And we can see that the large substituents coming off this double bond here, the methyl group as well as the longer alkyl, haloalkyl chain here, are both coming from the bottoms of that double bond. So this would be a cis molecule. The next one here, we see the hydrogens are already drawn in for us, and it looks like both of the long chains, both of the large substituents on this molecule are on the top side or going up, if you will, away from the double bond. So this would be a cis molecule. In the next 2 examples, we have our ring systems. We took a look at these at the end of the last chapter, and so we kind of should be a little familiar with them already. The first example here, we see a bromine atom attached to or bonded to a cyclohexane, and that bromine atom is coming out of the paper at us, so we might consider that to be the top of the ring in this viewpoint. And we have a methyl group going into the paper away from us, so we might consider that to be on the bottom of the ring from a top-down viewpoint, and they would be on opposite sides of the ring, the bromine would top, the methyl group on the bottom, making this a trans stereoisomer. And then in the example below, we see two different substituents on our ring. Both of them are pointing into the paper, so they are both on the bottom of the ring, making this a cis stereoisomer. So unfortunately for us, cis and trans stereoisomerism is not the only stereoisomerism that we're going to run into when we're looking at organic molecules. To talk about the other types of stereoisomerism that we're going to run into, we first have to talk about a property that some objects have called chirality. Chirality has to do with the mirror image of an object. All objects have mirror images. You can take any material object and put it in front of a mirror and you will see its mirror images. Where chirality comes in is whether or not those mirror images are superimposable on each other. You've got some examples here with a pair of tinted glasses put in a mirror. If both of the lenses are in the glasses, the mirror images would be considered superimposable upon one another. You could take the pair of glasses that is not in the mirror and orient them so that they look exactly like the pair of glasses that is in the mirror. But if you look at the pair of glasses on the right, where one of the lenses is missing, the right lens is missing in the actual object, but the mirror image has the left lens missing. So there is no way you could ever orient those glasses to represent or be exactly like its mirror image, because the right lens is missing in the actual object and the left lens is missing in the mirror image. Those two objects would be considered chiral objects or chiral representations of one another. Another good example of chiral objects are most people's left and right hands. They are, for the most part, mirror images of one another, but you can never turn your right hand so that it exactly matches your left hand. A lot of molecules share this property of chirality, and we're going to investigate how to represent that on paper, essentially. Here on this slide, we see some representations of how molecules can have this property of chirality. Chirality in a molecule most often rises when we have carbon atoms that have 4 different substituents. These are often called a chiral center, a stereocenter, or a center of chirality. Note, this can only happen at an sp3 hybridized atom. You may see a few other atoms than carbon. Phosphorus sometimes will show up as a center of chirality, but it's most often carbon, and almost all of our examples are going to be carbon. So when you're trying to identify a center of chirality, you're looking for a carbon that has all single bonds and has 4 different substituents to those single bonds. That means you can automatically discount any CH2 groups or CH3 groups. Those are always not chiral centers because they have 2 hydrogens or 3 hydrogens respectively, so they don't have 4 different substituents. Carbons in rings can be chiral centers if the 2 legs that are part of that ring trace around the ring differently. So you can see some examples that we have in the boxes here. We have an alcohol, and we see that the central carbon there is a chiral center or center of chirality because there are 4 different groups bonded to that carbon. There's a methyl group, an ethyl group, an alcohol group, and a hydrogen. And so there are 2 different ways you can represent that molecule that are mirror images of one another, that are not superimposable. They're drawn there, so you could never turn this. You can never turn that molecule on either side of that mirror plane so that they exactly match one another, and therefore they are stereoisomers of one another. They are different molecules, and when we write about them or represent them, we need to show that they are different molecules. We see some more examples down here in the bottom of finding chiral centers in bond line structures. The carbon here highlighted is chiral because it has a methyl group, an ethyl group, a chlorine, and a hydrogen. That's 4 different groups bonded to that carbon. The others are not chiral because this is a CH2, this is a CH3, and this is a CH3. So that's the only chiral carbon in that molecule. In this molecule, we have a CH3, a CH2, a carbon with an alcohol group, an ethyl group, a propyl group, and a hydrogen. So this is our chiral carbon in this molecule. This is a CH2, it's not chiral. This is a CH2, it's not chiral. This is a CH3, it's not chiral. In this molecule, we have some carbons that could be chiral, this one in particular, if the trace around the ring is different. So it has one substituent that's a bromine atom. There's a hidden hydrogen that would be a second substituent. The third substituent would be a trace around the ring this way, and we single bond, single bond, single bond, single bond, double bond, single bond. The trace around the other leg of the ring would be single bond, double bond. So those are different because you run into the double bond faster in this orientation than you do coming around the other leg here. So that trace around the ring is different for each of those legs, making this a chiral carbon. Note, remember, chiral carbons can only be sp3 carbons, so our sp2 carbons here are not chiral, and the CH2s around the ring are not chiral either. We do have an example of a non-chiral ring here. You might be tempted to think this carbon here is chiral, but if we trace around the ring for each leg, we find that the trace around the ring, because there's no substituents on that ring, is exactly the same for both of those legs. So that's like having 2 of the exact same substituent on that carbon. So that is not a chiral carbon in this example here. So on this slide here, we are going to see if we can identify the chiral carbons in these molecules. In the first example here, I am going to look at ascorbic acid or vitamin C first, and we can see when I am looking for chiral centers in molecules, I'm looking for carbons that have 3 bonds, or sp3 carbons that have 3 bonds, because I know sp3 carbons that only have 2 bonds or 1 bond, they're going to have 2 hydrogens or 3 hydrogens, and they're not going to be chiral centers. So I'm kind of looking for carbons that have 3 bonds or intersections where I see 3 bonds, and that one immediately jumps out to me for the ascorbic acid. So there would be also a hydrogen on that carbon there, and one substituent is an OH group, another substituent is an CH2 OH group, and then the fourth substituent is the big long ring structure there. So this would definitely be a chiral carbon in this molecule. The next intersection I see with 3 lines is this carbon here. So there would be a hydrogen there that we cannot see. One substituent goes around the ring and hits an oxygen first. Another substituent goes around the ring and hits an sp2 carbon first. And the third substituent goes up to the 2 alcohol groups on the molecule. So we have 3 different substituents there. We have the hydrogen there, that's the 4th different substituent. So this would be a chiral carbon in that molecule. This carbon here is a CH2, so it is not chiral. The carbon here is sp2. This carbon here is sp2 hybridized, so it is not chiral. This carbon here is sp2 hybridized. It is not chiral. This carbon here is also sp2 hybridized. It is not chiral. So the 2 filled in carbons are the only 2 chiral carbons in the molecule that we see there. If we look down, the molecule below it is mestranol. It says it is an oral contraceptive, and we're going to try to figure out if the carbons are chiral or not. We have a carbon here that is a CH3, so not chiral. We have a carbon here that's sp2, not chiral. 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 ch2, not chiral. ch2, not chiral. Now here is our first point of difference. There is our first possibility. We have a hydrogen there, and we have a couple of different legs that are all definitely different. If you follow those legs out from that carbon, I think it becomes apparent pretty quickly that those are all different. So that would be a chiral carbon in this molecule. This carbon here has the same situation. We have a hydrogen there, and then three definitely different legs being followed from that carbon. So that would be a chiral molecule. CH2 is not chiral. CH2 is not chiral. This molecule here is sp3, lots of complex legs and one lone hydrogen. I imagine it is a chiral carbon. This carbon here has 4 different legs, so it is a chiral carbon. CH2 is not chiral. CH2 is not chiral. This has 4 different legs, so it is a chiral carbon. And this carbon is not sp3 hybridized, not sp3 hybridized. So the highlighted carbons are the chiral carbons in mestranol. Moving over to fexofenadine, a non-sedating antihistamine, we will look at each carbon here. The carbons in the rings are all sp2 hybridized, so they are not chiral. The carbon here does look to have 4, actually you have to be careful, I almost made a mistake. So the 2 rings are exactly the same, so this is not a chiral carbon. This carbon here, so we have a hydrogen, and we have one substituent here that is this big long thing, all of this here. And then we have 2 legs, but the 2 legs would be exactly the same as they go around that ring and then follow down to the rest of the molecule. So that is not a chiral carbon. A CH2 here, a CH2 here, a CH2 here, a CH2 here. The nitrogen is sp3 hybridized, so it's possible the nitrogen could be a chiral center. We have a lone pair. We have a leg that follows down into the tail, but then we have 2 legs on that ring that would work out exactly the same. So the nitrogen is not chiral. The CH2 is not chiral. The CH2 is not chiral. The CH2 is not chiral. Here we have a carbon that has 2 different complex legs, an alcohol group and a hydrogen. So that seems to be the first chiral carbon that we run into. And then we have a bunch of sp2s that cannot be chiral. Then we have a carbon here that has 2 methyl groups attached, so it cannot be chiral. And then we have a sp2 carbon that cannot be chiral. So it appears as if the highlighted carbon here at the alcohol group is the only chiral carbon in this molecule. I'm going to leave the vitamin D3 at the top for you guys to do on your own. So a little bit more terminology here. 2 molecules that are mirror images of one another that cannot be superimposed on one another are what is known as enantiomers of each other. All chiral molecules have one and only one enantiomer. Enantiomers have exactly opposite configurations at their chiral centers. The easiest way to draw enantiomers is to flip all of the wedges and dashes in a bond line structure. And we'll look at some examples here on the next page. Here we have some examples of drawing an enantiomer. So in these molecules, luckily for us, most of the time when we see a chiral center, you have to indicate whether the substituents are coming out of the paper or into the paper to make the chirality of the molecule make any sense. And so you will see a wedge or a dash at chiral centers in chiral molecules. When you draw the enantiomer, which is the exact mirror image of that molecule, all you have to do is flip around the wedges and the dashes, or change any wedge you see to a dash and change any dash you see to a wedge. So when I do the enantiomer, when I draw the enantiomer for propanolonol, yeah, up here in the top left corner, I will draw the two phenyl groups. See how well my art is today. And where I have the hydroxyl group there on a wedge, I'll want to re-represent, change that around, and put a dash there. And that's how we draw the enantiomer of the propanolonol molecule that we have represented there. So the same thing would happen for the adrenaline. We only see one dash or indication of stereochemistry in that molecule. So this wedge here would be changed to dashes to show the enantiomer of adrenaline. For albuterol, you would just need to redraw this molecule and show that wedge as dashes to show the mirror image of albuterol. We have oxybutynin here in the bottom left corner, and if we want to draw the enantiomer of that molecule, we have to be careful. There is a wedge and a dash in this molecule, so we would just change this wedge to a dash, but we would also be careful to change that dash to a wedge. The perhaps toughest one on the homework is the bicyclic ring system, trying to draw the mirror image of that molecule. If you get something like that, all you can really do is just attempt to draw the mirror image of it. I'm not going to give you one like that on an exam, but there is one like that on your homework. So if you want to draw, it's kind of, maybe they give you kind of an easy one to do though. If you can draw that backwards, basically, something like this. That would be the mirror image of that molecule. And you can see how if I were to try to rotate it, I can never get the two molecules to orient in the same direction because they are chiral mirror images of one another. So at this point, I'd just like to take a second and make a point of note to talk about why chirality is such a big deal. We will see it throughout the rest of the course when we're talking about our molecules. We'll always have to be cognizant of the chirality of the molecules. And as you go further into science, you will see chirality is very important to biochem and metabolism. So a lot of the molecules that we encounter in organic or natural products have chirality. We have an example here. The odor that you smell if you crush up spearmint leaves is a compound known as R-carvone. There is the enantiomer of carvone, the S-carvone, has a completely different odor that we associate with something called caraway seeds. And they're both reactive to the cells and the active sites in your nose, but just that difference in stereochemistry gives them completely different smells. And a lot of our biologically important molecules, sugars, amino acids, enzymes, etc., all have chiral centers or all have chiral arrangements and will act in our body in different ways if we don't get the right or correct chirality of a molecule. I've got an example here, one I've noticed recently. So a lot of times drugs have an active enantiomer and an inactive enantiomer. And one of the things that we'll talk about going forward is in reactions, in chemical reactions, a lot of times it's hard to design a chemical reaction that gives you only one or the other. A lot of times your chemical reactions result in a mixture of both, what's known as a racemic mixture, an even 50-50 mix of both. Zyrtec has been an allergy medicine around for a really long time, or I say really long time, maybe 20 years now, and it works really well, but it's always been sold as a racemic mixture of this particular molecule. A couple of years ago, a new drug Zysol hit the market and was really kind of took off and talked about how good it was working by a lot of doctors and things. And I just got to looking at it, and it turns out all that happened was some manufacturer figured out how to separate the active enantiomer from the inactive enantiomer, and so they sell the active enantiomer only as the preparation known as Zysol. And so they're the same drug, it's just that Zyrtec is 50-50 active and inactive enantiomer, both molecules of the mirror images of one another, where Zysol is the only the active enantiomer in pill form. Somebody figured out a way to separate it, which is not always the easiest thing to do. So now we can talk about how we designate chirality with our naming system in chemical nomenclature. And to do so, we use something called the Cahn-Ingold pre-log system, or perhaps the R and S system for chiral nomenclature. To use the Cahn-Ingold pre-log system, we have to learn to assign priority to each substituent on the chiral carbon. We assign priority highest to lowest, 1, 2, 3, and 4. The highest priority is 1 down to the lowest priority of 4. We assign priority by atomic numbers. So we look at each of the things bonded to that carbon and we assess what their atomic number is. We look at their position on the periodic table. Things with higher atomic numbers get higher priority. If there is a tie, you move further down the bond chain until the tie is broken. You always look for the point of first difference. To determine whether a molecule is R or S configured, you make sure the lowest priority, number 4, is on a dash turned into the paper, and you look at the orientation of 1, 2, and 3. If 1, 2, and 3 rotate counterclockwise, we call that an S configuration. If 1, 2, and 3 rotate clockwise, we call that an R configuration. So we have an example here to show you how this is done when you have to go further than just the first carbon out, because that's when it gets a little tricky to assign these priorities to these molecules. In the molecule that we see there, we have an alcohol group and a couple of carbon chains, as well as a hydrogen leading off of this chiral carbon. So our chiral carbon is going to be this carbon here. And we're trying to determine what is the priority of each of the substituents coming off of that carbon. So if we look, we have a hydrogen, an oxygen. Oxygen is going to have the highest atomic number, and hydrogen always has the lowest. So our hydrogen is definitely going to be 4. Our oxygen is definitely going to be 1. We're trying to figure out which carbon chain is going to be 2 and which carbon chain is going to be 3. So we go and we see the first carbon here has 2 hydrogens bonded to it and 2 hydrogen bonded to it. So there is no difference as of yet. We have to go to the next carbon down the chain. And if we look at the next carbon down the chain, we list out what's bonded to each of those carbons. And we see this carbon has a carbon and a hydrogen bonded to it. This carbon only has 2 hydrogens. So this is the first tiebreaker that we come to. And so this will have the higher atomic number. And so that will be the higher priority group. And so when we look at this molecule, this will be the second priority, and this will be the third priority group or substituent on our chiral carbon. As a point of note down here, you'll see at the bottom, as you're moving along these chains, if you run into a carbon that is double bonded, so for instance in this example we would be trying to figure out the order of priority for the substituents on our chiral carbon that I highlighted there. But when we move to this carbon and try to make a list for this carbon, we see that it's double bond. We want to make sure that the list counts the double bond twice. So that would be a pretty high priority carbon because we would run into those oxygens twice. So one of the hardest parts of assigning RRS when you're writing these molecules and designating their chirality is trying to get the lowest priority group on a dash if it is not there already. If the lowest priority group is not on a dash, you must rotate the molecule either by redrawing it or in your head until it is before you can decide if 1, 2, and 3 are clockwise or counterclockwise. If the 4 is not on a dash, if it's on a wedge or on a line, you might get the wrong R or S configuration, and you won't as long as the 4 is always on a dash. So you have to rearrange that molecule spatially in order to determine its configuration. Luckily, there is a shortcut given to us here in our text, and I'll talk about that on the next slide. So I saw this shortcut in this text, and it was the first time I had ever seen it, and it really does make assigning RNS much easier than the way I was taught back in the day, which was what you saw on the previous slide. You got to switch it around, redraw it, and all that kind of stuff. The easy way to do this, the shortcut way to do this, is go ahead and assign all of your priorities in the molecule. If the priority number 4, usually a hydrogen, is not on the dash, switch it with whatever is on the dash. And then switch the other 2 substituents as well. You have to switch whatever is left over. And then you can determine if it's clockwise or counterclockwise. That's all you have to do to determine whether the R or S configuration is present at a chiral center in a molecule. Of course, we'll look at some examples on the next couple of slides. So we have an example here. We're going to see if we can identify the chiral centers and determine whether they are R or S. And if we look at our molecule here, try to figure out, first of all, are the pointed to carbons chiral or not? And carbon number 1, turn my pen on here so the page doesn't change. Carbon number 1 is an sp2 carbon, so it is not chiral. Carbon number 2 is also an sp2 carbon, so it is not chiral. Carbon number 3 does appear to be an sp3 carbon with 4 different substituents, so it is a chiral molecule. Carbon 4 is an sp3 carbon, however it has 2 hydrogens, so it is not chiral. And carbon 5 does appear to have 4 different substituents, so it is chiral. And it's not pointed to, but just for posterity, this carbon does have sp3 hybridization, but it doesn't have 4 different legs since 2 of the legs are methyl groups, so 2 of the substituents are the same. It is not a chiral carbon. So let's try to evaluate 3 and 5 and see if we can determine their configuration. So the way I do this is, first of all, I like to assign the priority, of course, first. I look at the substituents on my number 3 carbon, and I see one of them is a chlorine and the other 3 first arrive at a carbon. So the chlorine directly bonded to that carbon is going to be priority number 1. And then if I list out the carbons, what the carbons are bonded to on these next few, then I see, if I look at this carbon, its list is bromine, hydrogen, hydrogen. If I look at this carbon, its list is chlorine, carbon, carbon. And if I look at this carbon, its list is chlorine, or carbon, excuse me, hydrogen, hydrogen. So bromine has the highest atomic number out of those 3 lists. That's the first point of difference I see, is a bromine, a chlorine, and a carbon. So bromine has the highest. So this will be priority group 2. This will be priority group 3. And this will be priority group 4. I like to pull the chunk that I'm looking at out of the molecule and redraw it a little more simply. So if I leave off all of the convoluted stuff, just that carbon has these things oriented around it. It's got a wedge and a dash at the top like this, and it's got some legs with some substituents with some other things. And then I like to write those numbers there in those positions. 1, 2, 3, and 4. So now I can perform the shortcut that I talked about on the previous slide. So to perform the shortcut, what you do is you look and see, is 4 on the dash? In this case, it's not on the dash. So we're going to switch 4 with whatever's on the dash. So I'm going to redraw that carbon in particular here. Put my wedge and my dash and my 2 substituents. Except now I'm going to put 1 here and 4 here. Now the shortcut also says that I have to switch the other 2 substituents also. You have to. So that means 2 will be here and 3 will be here. Now we can stop and see, are 1, 2, and 3 clockwise or counterclockwise, and that will tell us if it's R or S. So I see here 1, 2, and 3 is clockwise. So that carbon has an R configuration. If we look at the next carbon, I'm going to clear off everything on this slide so that we can see it a little more clearly. If we look at the next carbon that we determined was chiral, carbon number 5, we might find it's a little more tricky. We have to have some previous information in order to determine the chiral configuration of carbon number 5. So I'm just going to redraw it out here. This carbon has this configuration. So there is a bromine atom on a wedge down here, 2 alkane chain substituents on the top lines. Now you have to know there is a hydrogen on a dash next to the bromine. If it's not there and there's a wedge drawn, no dash drawn, and 2 solid lines drawn, then that means the hydrogen has to be on a dash behind the bromine. So now we need to assign priority of these chains. If we probably can already see that the bromine atom is going to be priority number 1. The hydrogen, being it has the lowest atomic number of all atoms, has to be by necessity priority number 4. And then the question is, what is the priority of the 2 chains? So this chain has a 1, 2, 3, 4 links before we get to a chlorine, where this chain has 1, 2 links to a chlorine, as well as methyl groups in these positions. So I feel like that's going to have higher atomic numbers, and if you make every list you would see. So this would be priority group number 2, and this would be priority group number 3. So if I look at the representation that I've drawn outside of the molecule over here, I can rewrite my numbers. 1, 4, 2, and 3. Now, luckily for this molecule, number 4, the hydrogen, is already on a dash, so we don't need to perform any switching or flipping. We can simply look and see what is the counterclockwise or clockwise-ness of 1, 2, and 3 and determine our configuration from that. So we see 1, 2, and 3 in this case goes counterclockwise, meaning that carbon number 5 has an S configuration. So now that you know how to designate a carbon as having R or S configuration, we'll talk about how we use it in our IUPAC nomenclature system. When naming a chiral compound, the configuration of the chiral center has to be indicated at the beginning of the name, in italics, in parentheses, and followed by a dash before you start writing the name. If you have more than one chiral center in a molecule, you have to provide the locant of that configuration to say, hey, the chiral carbon at 2 is an R configuration and the chiral carbon at 3 is an S configuration, for example, in the molecule given here. Here on this slide, we have a little bit more terminology. Now that we've talked about chirality and its configurations, let's add one more definition in there, and that is for diastereomers. So we've talked about how stereoisomers are non-superimposable mirror images of one another. We can go further than that, and we can have non-superimposable molecules that are not mirror images of one another, known as diastereomers. You run into diastereomers when and only when you have more than one chiral carbon in a molecule. If there is only one chiral molecule, then you only have that molecule and its enantiomer. When you have more than one chiral center in a molecule, then you can have many different arrangements or many different combinations of S's and R's. And those different combinations of S's and R's are how you get diastereomers of different molecules. We'll take a look at a couple in the next few slides. So on this slide, we'll take a look at a difference between enantiomers and diastereomers, and we can see this molecule here would be called 2-cyclohexanol, and we can see that the carbons at 1 and 2 would be chiral carbons, and so we could, if there were wedges or dashes shown, we could assign R and S to these different carbons. And in fact, there are 4 different combinations. Remember, we have 2 chiral centers, so there are 4 total. 2 to the n, 2 square is 4. So there are 4 total combinations of R and S configuration for these 2 carbons. So if one of them was, if carbon 1 was R and carbon 2 was S, then the enantiomer of that molecule would be the exact opposite, 1s, 2r. These 2 molecules here, these 2 representations here would be enantiomers of each other because they also have 1r, 2r versus the complete opposite, 1s, 2s. However, this molecule here, that is 1r, 2s, is not opposite of, say, the end molecule down here, that is 1s, 2s. To be opposite, we would need 1s, 2r, but instead we have 1s, 2s. These 2 molecules, they are considered stereoisomers of one another, but they are not enantiomers. They are diastereomers. So the way you tell the difference, enantiomers always have exactly opposite configurations, whereas diastereomers are the same molecules with just jumbled up configurations from what we see. It's not exactly opposite. Only the enantiomer is exactly opposite. Diastereomers are any other random mix of different S's and R's for the same molecule. Here we have some more examples. In this case, we have a molecule with 3 different stereocenters. So of course we can have 2 to the 3rd, or 2 times 2 times 2, for 8 different combinations of S and R for these 3 chiral centers. And you can see all 8 combinations, and inside the boxes are the enantiomers of each of the molecule. In this case, we have 1R, 2R, 3S. And the exact opposite is 1s, 2s, 3r. So these 2 molecules are superimposable mirror images of one another, making them enantiomers. This molecule, compared with any other molecule in any of the boxes other than the one it shares, would be considered diastereomers of the rest of the molecules. Everything inside the boxes shares physical characteristics. This molecule and any of the other molecules will not share physical characteristics. Here on this slide, we have some examples to determine whether the represented molecules are enantiomers of one another or diastereomers of one another. And to do that, we can rely, for the first set of molecules, we can rely on some of the first information we got back earlier in the lesson. We remember that to draw the enantiomer of a molecule, all you have to do is take all of the wedges and flip them to dashes, or vice versa, to get the enantiomer of a molecule. And we can see that in this molecule they are drawn the exact same way, except for in representation 1 we have 2 wedges, and in representation 2 one of them has been flipped to a dash and one of them has been left a wedge. And since to draw enantiomers you always flip every dash to a wedge, we can feel pretty confident in saying that those two molecules are not enantiomers of one another, but these two would share a diastereomic relationship, and so these two molecules are diastereomers of one another. Now, doing this for this molecule here is not quite as simple, because you'll notice what they've done is they've twisted that single bond so that now the methyl group that was in the plane position is now in the push forward position. So the best way to do a molecule like this is to assign R and S configurations to the two chiral carbons and see if they are exact opposites of one another. If they are exact opposites of one another, they are they're enantiomers. If they are not exact opposites of one another, they are just diastereomers. So we'll do that now. We'll look at each of these carbons here. We can see that this would be, these are a little bit simpler. I'm going to assign, so we can't see the hydrogens there, but I will put them there. And luckily for us, in both of those examples, the hydrogens are already on dashes, so that puts our 4s probably already on dashes, which is good. Same here, we have an H here that is not shown, and we have an H here that is not shown. So they were nice to us there, and they put the 4th priority group already on a dash. It looks to me like this would be priority 1, this would be priority 2, this would be priority 3, and this would be priority 4. So it looks like 1, 2, 3, this is R. And in the second carbon, this is 1, this is 2, this is 3. 4 is already on the dash, so we can just compare. This looks like R as well. It is clockwise. 1, 2, and 3 is clockwise, so both of those are R. So if the next molecule is an enantiomer, both will be S. If it is anything other than both being S, then that is either a diastereomer or the exact same molecule. We'll figure it out. So our 4 is here on this group, our 1 is here on this group, our 2 is here on this group, and our 3 is here on this group. So that would twist this way. This would be an R configuration carbon. This 4 here, the chlorine would be 1, the longer tail would be 2, and the methyl group would be 3. That orients 1, 2, 3 counterclockwise, so that would be S. So the first molecule has RR configuration, the second molecule has RS configuration. That is not exactly opposite. It is different, however. So they are not enantiomers, but they are diastereomers of one another.